Hello again. We are still in chapter 2 considering the application layer of the communication stack. In this recording we continue with the section 2.6 peer-to-peer applications, and we will overview the very important component of peer-to-peer application that allows indexing of the information that is shared between peers. So we will talk about distributed hash tables. So think about the following problem. We have a peer-to-peer network, so all peers contain an information that we are potentially interested in. The question is, how do we find where the interesting to us information is located? One possible way of handling the situation is to have a dedicated server, like a tracker in BitTorrent system, where peers would register what do they have, and where we can send our queries about resolving the addresses of the peers according to some value. But what if this centralized solution is not an option? So what if we do not have a dedicated server that keeps the index of the information? Instead, we have this index in a distributed table. So each peer contains part of the index database. Then we need a special mechanism on how do we send the request with the specific information that we are looking for, and how this request is propagated in the network, and how the value is returned to us. Different approaches to handling distributed index tables, like early peer-to-peer applications such as Napster. They used flooding mechanism when peers wanted to find some information. Flooding means that whenever we want to find something, we broadcast the request. And all peers that hear our request rebroadcast this request. And in this way, we flood the network with the request about a particular information that we are looking for. However, as you may easily imagine, this solution is not scalable. Distributed hash tables, on the other hand, is an alternative way for efficient indexing and searching information in peer-to-peer networks. DHT is a distributed peer-to-peer database. As any database, it keeps the key value pairs. So what is a key? Key is something that identifies the value. An example of a key would be a social security number with the value be a name of a person registered with this social security number. In the case of peer-to-peer network, a key would be an identifier of a content that we are looking for, and the value would be IP address of a peer that keeps it as a whole or parts of it. So as any other database, DHT should allow peers to query database with the key, and database should return values that match the key. As well as peers should be also able to insert new key value pairs. The way how distributed hash tables implements indexing through through maintaining key value pairs is rather straightforward. Assume we have n bits to represent our identifier. It means that our identifier range is between 0 and 2 to the power of n minus 1. We require that the key should be chosen from the same range of integers, from between 0 and 2 to the power of n minus 1. The way to implement it is to apply a hash function that takes any value as an input and maps it into an integer in a given range. That is why this way to implement a peer-to-peer database is called distributed hash table. Let us assume for a moment that we have a set of computed key value pairs, where the value would be, for example, a name of the file that we store in a file sharing peer-to-peer network. And the keys would be the results of computing the hash function based on the name of the file. So now the central issue in distributed hash tables is how to assign the key value pairs to the actual peers. Because, as you may imagine, certain peers with exactly the same key may not be present in the network. So the rule here is to assign a key to the peer that has the closest ID. And in the context of the distributed hash tables, the closest ID would be the immediate successor of the key. So here's a simple example. So assume that our identifiers have 4 bits. It means that the identifier range is between 0 and 15. So also assume that at this particular moment we have peers 1, 3, 4, 5, 8, 10, 12, 14 being present in the network. It means that we are missing what? Peer number 0, peer number 2, 6, 7, 9, 11, 13, and 15. These peers are missing. So now we compute a key for a given name of a content. We compute a key equals 13. So in our case, the successor peer would be 14. So we would store this content in peer number 14. If by any chance by a result of computing the hash function we've got the key 15, again the peer with identifier 15 is not present in our network, so the immediate successor of the key would be 1. Successor peer would be 1, and the content will be stored there. Alright then, so by now we know how to map a value to a key and how to map the key, the computed key value pair, to a specific peer. Now the question is, how do we search for the information? In order to answer this, we need to first consider how do we arrange the peers in a sort of topology on which we can perform the routing of the requests to find a specific information. So DHT, distributed hash tables, implement a circular topology where the nodes are arranged in the order of increasing identifier, and the node with the peer with the highest identifier references the peer with the lowest identifier. So by this the circle is completed. So we will call this topology an overlay network. So let us demonstrate now how a specific resolution request would travel in such an overlay network. So the assumption also here is that each peer is only aware of the immediate successor and the immediate predecessor, the identifiers of the immediate successor and the predecessor peers. So assume that peer number 2 has got a request who is responsible for the key with this value. In decimal, this key would correspond to number 14. So, and here the nodes identifiers are exactly the same in decimal as on this previous slide. So remember, so 1, 3, 4, 5, 8, 10, 12, 15. So, and now we are looking for an entry or for a peer who is responsible for an entry with the key 14, 1, 1, 1, 0. So, obviously the node number 2 is not aware, it doesn't have this information, so it forwards the request to the next neighbor. Do you have this information? No, I don't. So the request travels along the circle until it reaches the peer number 15, which apparently is responsible for this entry. And peer number 15 would respond back to the request initiator that I am responsible for this key value. So very efficient search mechanism, so which on average requires in order of n messages to propagate a request in a network with n peers. Further optimize the searching, the performance of the searching procedure by making the peers to remember not only the successor and the predecessor, but also some shortcut peers, the identifiers of the shortcut peers. So in this case, we may drastically reduce the number of messages that are sent in the overlay network. So we may achieve this complexity of logarithm n messages in a query. So let us now consider a problem case. So assume that a node number 5 leaves the network. So we need that the network would self-reorganize itself in order to keep the functionality going. So how do we do so? In order to deal with the situation, it is required that every peer keeps an information about its two successors. So, for example, node number 4 keeps an information about successor node number 5 and the next successor node number 8. Periodically, all nodes in the network would ping its immediate successors in order to check whether they are still alive. So, in the case when node 5 leaves the network, as is very typical for peer-to-peer applications, so peer number 4 will eventually realize that that peer number 5 disappeared, and it will request the successor of node number 5 about its own successor. So the peer number 4 will make peer number 8 its immediate successor and will keep the identifier of peer number 10 as the two-hop successor. So in this way, the topology is restored. And in the class, we will see how the network should react where a new peer would join the network. With this topic, we finish an overview of the main mechanisms behind peer-to-peer applications. And in the next recording, we continue with some basics of socket programming with TCP and UDP protocols.